Okay. Well, welcome to this webinar. My name is Ryan Mayfield. I'm joined with Greg Smith from Tigo, and we're going to talk today about optimizing design to avoid crosstalk. And, crosstalk, we're going to get into, kind of what it is, how it affects PV installations, and quite honestly, how it affects other types of installations as well. So it's kind of a big issue when it gets to communications for module level power electronics. So I'm glad to have Greg along with us to talk about that.
Yeah, awesome. Thanks, Ron. I always love working with you guys and your team there at Mayfield Renewables. I appreciate you guys putting this together for us.
Great. Thank you. There we go. So again, my name is Ryan Mayfield. I'm the founder, CEO of Mayfield Renewables. We're a technical consultancy. So working with Tigo on putting this training together. I've done lots of other trainings with NABCEP and other types of entities. So I'm glad to have you here. Greg, you want to introduce everybody for those that don't know you already?
Sure. So I started out in the industry at SMA back in 2008. And that was when I met you, Ryan. So we go a ways back. I spent about 7 years there. Then I went to Sonnen and helped them launch their storage product in the United States. I was there about 6 years and then made the move to Tigo. And so, it's the same story. Everybody in the industry eventually puts on a different color shirt and we just kind of keep on rolling. But in the United States for Tigo, I'm the director of technical training. I mostly train internal people, so sales and sales engineers.
Okay, cool. Yeah, and so you've been doing training for a long time. So this is, I always enjoy going to your classes and sitting in and trying to heckle when I can, but it doesn't ever seem to work out. So, okay, so let's jump into this. So what is power line communication? So actually, maybe we should back up even a little further. So, the title is, avoiding crosstalk and, doing better designs with to avoid crosstalk. And so we'll get into exactly what crosstalk is, but first and foremost, the reason this is an issue is that we are communicating, having components communicate on power lines. And so, power line communication, and what we're doing is we're using the conductors that carry the electrons, it's where the current's flowing for our, in our case, PV systems, but this can be used, it is used in home automation systems. It's used in lots of different applications, elevators, smart houses, street lights. So they're all kinds of applications. And the idea here is that we're using conductors that are already in place, and so power line communication, we are communicating over the power lines. I don't know if you wanted to add anything to that one, Greg.
No, that's basically, it's an ingenious method of communications. As you said, you're using existing lines, and it's been used in our industry for quite some time now. So it's not new; it's been around.
Yeah, exactly. So it's not a new concept or anything, but just want to make sure, when we talk about PLC, power line communication. And so just kind of a visual effect here, you have your current carrying conductor. Imagine that is, in your home. This is the, the NM cable in your house. This is the USC2, the PV wire running up in your PV array. And you have some sort of transmitter. You have something that is creating a signal, and that signal is going to get induced on the line. So we have a transducer that, is connected to the transmitter, and that is it's putting a signal, and we're able to induce that onto the power line communication. I say I don't do it. Other folks, the smarter folks out there are doing this. And so inducing this signal on the current carrying conductor. On the other end of this current carrying conductor, wherever you want it, this is your smart light, this is your smart home TV, whatever it is, you have a receiver. And that receiver is going to recognize that whatever that signal is, it's going to take it, and whatever that signal is being produced by the transmitter, it's telling the receiver to do something, turn on the lights, do something with the TV, whatever it is. And so the signal can be received, it decodes it, and it does whatever it is that it's supposed to do. So relatively, it seems simple, straightforward. I know it's not, it's relatively complex, but in essence, it's a pretty straightforward process.
Yep, absolutely. I like it. Love y'all's animations and diagrams. They just get the picture just
Cool.
right there, like,
Yeah. Yeah. So that's kind of, just kind of what it in a visual format. And so here's another way to kind of, it helped me. And this was something, Greg, you and I were talking about. And when we were talking about it, and it's kind of, I know people like to dive in and kind of get a little bit more, maybe a little nerdier about it and stuff like that. And so another way to think about it is kind of how it would look on maybe not necessarily a scope, but just kind of what these signals look like. And so here we have this graph on the top. And so same kind of concept, or we're showing the same thing on the bottom as what we just went through. But on the top here, we have kind of a graph of what it would look like. And so you have your transmitter that's doing a modulated data signal. And so that's something maybe, Greg, you want to talk a little bit about is something when we were preparing, you were talking about the modulated data signal. So the transmitter is putting out a signal, and exactly how is it? I mean, what is it doing there again, Greg?
Yeah, dude, this is so cool, because now you're getting back into my pre-solar industry days when I rode, nuke subs for 20 years as a sonar tech, right? So the same things that we're doing here, we did the same things on our underwater, basically underwater telephone. Yeah, and so we would communicate with another submarine underwater. And so we were using water as the medium, not a copper wire. But the concepts are still the same, right? You wouldn't want somebody, if a bad guy was out there, you wouldn't want them, another submarine that's always listening to hear what you're saying. So there's different types of modulation. There's amplitude modulated, there's frequency modulated, just like on your radio, right? Mm-hmm. AM, FM. So we're doing the same thing here. And so I think you're going to get to it later on, but you basically have a carrier signal that all the information attaches to. Yeah. And so that carrier signal is what the encoding is from the previous slide. And so unless you have, perfect. Yep. And so unless you have the, what was that from A Christmas Story? The decoder ring, right? Unless you have that, you don't know what that is saying, right? And we heard it all the time just playing with our allies. We'd hear, but we didn't understand what they were saying because we didn't have the same carrier, right? So in a very simplistic way, all the information is attached to this carrier signal. And so that is why the communication from this power line does not interfere with the electrical, the EMF that's pushing through those lines at the same time. They're two different frequencies, and somebody figured all this out a long time ago and was able to put it into these types of systems.
Right. Yeah. And so then on the other end, when it's getting received, that the receiver's decoding it and is able to make sense of whatever that signal was. So this kind of just helps, and we're going to build on this here in a little bit when we get into, what are some of the, what can happen or what can go wrong, I guess. But this is, how it's supposed to work and how those modulations get decoded on the back end.
Yeah, and this is something you don't have to worry about, right? As an installer or a user, this is all way down deep into the device's hardware and software schemes. You just plug it in and it just goes. Like, that's all you have to worry about.
As long as you install it right, because you can't.
That's right.
So yes, yes, you don't have to worry about it. You don't have to worry about it. It's a lot like with your grid tie inverter. It's UL1741 listed. You don't need to worry. It will disconnect from the grid when the grid goes out. You just have to install it right. You have to do it right, and it will do its job. So before we get into that stuff though, why would we do this? What are the pros? There's always going to be pros and cons of everything. So we have to, or the pros side of it, you're eliminating signal wiring. You don't have to install a bunch of Cat5 everywhere or whatever signal conductors that you need to. It reduces installation time. And then I think this one's a pretty big one too, because, a lot of times you can use wireless communications to do the same thing, get transmitters, but you can get up on, we're focusing in this class, in this course, we're talking about probably really most commercial roofs and larger installations. So you can get into situations where you got a bunch of stuff up on a roof, or it's just wireless is just not an option. So you already have to carry that power. So why not use those lines to help carry your data as well? It's kind of one of those, the pros of it all. And then on the con side, as we were just talking about, it's, susceptible to noise. And so noise being electrical noise. And so the signals themselves, if you're not careful, can get crossed up. For those of you that remember, having a TV set that looks like this, you get kind of the fuzzy output on it. And it's difficult to fix that after the installation. So if you get some noise on the lines because of conductors, as we'll talk about here in a little bit, maybe the conductors are too close together. It's kind of a pain in the butt to separate those conductors after the fact. And so it does become, that can be a con side of it. And then fixed location of equipment, you can't, the equipment is where it is. And so you can't easily move things around to try and mitigate any issues after the fact.
Yeah, it's much easier to do it right the first time. The previous company that I worked with had a storage system that worked with home automation networks. And so for the first time, energy storage systems were having to deal with this, weird kind of home automation stuff. And even home automation's been around a long time, since the mid 90s or so. And even them, like the high frequency lighting is like in the 200 kilohertz range. That kind of messes with the whole modulation, right? So it's not like a foolproof thing. And so there's a whole lot of stuff, and all that happens in the design stage, which we'll get into later. But yeah, you just never know, right? But the more you can do up front, the more you know about the site, and the more apt you are to just fend all these issues off in the first place.
Yeah. I totally remember. I remember now if those were a bunch of filters. I remember like having to get filters and installing filters and things like that when people were doing their home automation and trying to do some of this stuff in the early days. Yeah.
When they would turn something on, like a blender, and it would mess with it.
Yep.
Yeah.
Yeah. Kind of bringing back all those memories.
Oh, no.
Okay, so let's get into, what is crosstalk then? So we've kind of alluded to it a little bit here. So, what we have here is that same thing we've been showing you. So we have a transmitter, we have a receiver, everything's fine in the world. When you have this single transmitter, single receiver, there's no issue because everybody's happy, everybody's getting the signal and understanding the signal that they want. So what can happen is you introduce a second transmitter and a second receiver. And if you are running those conductors, if they're too close together in this case, the power lines are running in the wall together. It's, because when they roped the house, they ran all the Romex together, and now you're trying to do something on two different circuits, or probably, maybe even they have, it's the single Romex with the two hots and a single shared neutral. So they're right next to each other. What ends up happening is the signal, those modulations basically start to interfere with each other. I mean, they're getting induced on the power line. So, signal one is getting somewhat induced over onto that, where signal two on the signal two wire, and they're starting to get mixed up. And so, Greg, I really liked when we were prepping for this, you were talking about the radio, kind of the radio situation. So, you have two different radio stations. You're driving from one location to another, and you're getting just out of the reach of one radio station. You're picking up on the same dial, a new radio station. So you're getting both, I guess you're getting both country and rock or something on the same station. You don't quite understand what you're listening to, but you kind of get a little bit of each.
Yeah. That was the best analogy, only because I live it every time I go to the Campbell office. I listen to one station here, and right when I get into the mountains going into the Bay Area, it's just like I said, they start mixing, and you end up getting frustrated and just turning the thing off altogether, right? So same thing with this.
Yeah, right, exactly. So you end up turning it off because it's not working, and so you just end up, doing whatever it is yourself, whatever it was that was supposed to be automated for you. In a home automation type situation, in a PV system, you're not going to be so lucky. It's not going to, you don't get to just, ignore it and deal with it yourself. So, so we'll talk about some of those things that you do to change that. So looking at, just for those, this view really helped me as well when I was doing some research and looking at this kind of view of the whole thing just really clicked for me. So to show it for those folks that are, kind of thinking the same way, here's that same modulated data that we showed you earlier, and it gets induced on the line and then gets extracted at the other end. What can happen is if you get those lines that are too close together, you see that line 1 and line 2, they really have the same signal that they're putting out. There's really no difference there. The issue is that they're on a different timeline. And so you put them on, you get those both superimposed on their power lines. Those power lines get close together. They're in that third section. And then they start to talk to each other. That's what we're talking about, crosstalk. They're talking across the different lines. Gets over to the receiver. Receiver tries to grab that data, and it has no idea. It's not even talking anything anymore. So it doesn't know what to do with this information.
Yeah. Either way, right? It's either the receiver is only picking up bits and packets of what it's supposed to get. And so maybe you have this corrupted data that, maybe the lights flicker or something like that, or worse, the two signals cancel each other out and then nothing works.
Right. And so, I guess that's the kind of the almost worst case scenario, right? They completely cancel each other out, and then it doesn't even know what, or it doesn't work at all. Yep. Okay. So that's anything other on crosstalk or anything else on just these signals that you wanted to say, Greg, before we move into, so now we're going to move into talking about how this really applies, to PV systems using PLC. So I don't know if you wanted to give anything else on these, or are you ready to?
I think we geeked out way too much on this for most people, but I love it.
Okay. Well, then let's move on. If you're saying we took too long, then we took too long. Okay, so PLC applications and PV installations. And I just want to, kind of point out or reiterate here that this is not a Tigo specific phenomenon. This is not something, I'm here talking with Greg from Tigo, but it's really anything that's using PLC to communicate between different components. And so, if you're using other components, it's just as much an issue over there as it is here. And so we're going to just talk about kind of big picture, how you can avoid things. Tigo has some specific things. So we'll definitely touch on those as well.
Yeah. And just to kind of, when I started with Tigo in 2021, and the first NABCEP, go to that's just a family reunion, right? And everybody's like, "Oh man, Greg, you got a green shirt on, like what's going on?" And like some of the first things that people, they're like taking their phones out. I'm like, "Oh, dude, man, I use Tigo. I got," and this is like taboo, right? Like no manufacturer wants to talk about this, but I will, and I'll suffer the consequences later. But they're showing me like pictures on their phone of a TS4 with a hotspot burnt up. I'm like, whoa, dude, that's not good. That's not good. And I think I'd only been with Tigo a week before that NABCEP conference, right? So I'm like, oh man, I got to check this out. And so I'm talking to the service people and the sales engineers, and it's not a Tigo thing. It's not. Mm-hmm. It's anybody that uses this technology. Yeah. And so I learned a whole lot about this, but we'll get further into that as we go along. But I just wanted to preface it with that. It is not a Tigo issue.
Right. So real quick, just this is not going to happen, and maybe I'll try and push this a little faster here, but this is the same thing what we've been talking about here. So first off, I would say this is not the only use of PLC in PV systems, but this is a pretty big one. And this is all over on the DC side, and it's all around rapid shutdown. We won't get into, the ins and outs of rapid shutdown, all that kind of stuff. I'm sure folks that are listening in on this understand, probably fairly well, rapid shutdown, kind of why we need it, how we're accomplishing it. And so when we're using module level power electronics and we add these PLC transmitters, what we're doing is we're inducing that signal onto the conductors so that we can control the rapid shutdown devices, or control the circuits. Ultimately, that's what code is saying, is that we have to do is we have to control the circuits, and this is giving us a way of controlling the circuits to meet the rapid shutdown requirements. And so the conductors are run through the core. This is, and we'll get into, how many conductors, we'll get into some installation specifics, but just, kind of set the stage here. We have conductors, we have some sort of transmitter, has a power source to it. This can look a lot of different ways. It's integrated in the inverter, it's external to the inverter. We're showing it all external to the inverter, but there's plenty of options where it's integrated in. And so the conductors are coming in, and then that signal, you can see it's getting induced onto power conductors. I'll repeat this again later, but also just when you're doing this, you see we're showing it going on the positive. It can go on the positive or the negative, but not both. So it's kind of, dealer's choice in that sense, but don't put it across. Don't put both conductors from that circuit through there. It'll cancel each other out, and then it's just not going to work. So just something to point out there. And again, we have another slide and we'll repeat that again later. Okay. So let's talk about some specifics on some specific applications. And so single inverter, single transmitter, maybe a small number of strings that are coming into this. Maybe it's a relatively small installation. Again, we'll show this again later, but you can actually do up to 10 strings. Is that right, Greg?
Right.
So you can put 10 conductors through that CT, which is going to equate to 10 strings. And so you can actually have, a relatively large array on a decent size inverter that is supplied from a single transmitter. And it's okay to run all those conductors together because you have a single source. Even if you had 10 conductors running through that CT, they're all getting the same signal. There's nothing there there's no crosstalk to be had there because there's only a single signal that's going out. So if that's your case, have at it, run them all together in the same conduit and the same cable tray, whatever it is that you want to do. It'll be fine because there's no source of crosstalk there.
And the 10 conductors, Ryan, the 10 conductors is our limitation.
Okay.
So that may be somebody else, maybe more, maybe less, just depends.
Okay, thanks. Thank you for that clarification. So yeah, so read the manual, part of the presentation here.
Right.
So thank you for that. Tigo has a 10 conductor limitation. Others may be different. So understand if you're using somebody else, what your limitations are there. Real quick, I want to go through what happens here when kind of how the rapid shutdown is getting enacted here. And I just kind of want, and this is true for all of our upcoming situations. This is just the easiest way to show it. So I'm going to go backwards one. So here's our, regular situation. Everybody's up and happy. We have power to the transmitter. We have our interactive inverter. And then what I want to talk about here is what happens, or how does the module level power electronics, how do they react, or how are they, controlling the conductors? And so the idea here is that we have a power supply fed from the utility, same thing that's feeding the interactive inverter. And the other thing I should note is, well, I'm gonna progress through these slides, and all of this is instantaneous. They all happen pretty much at the same time, but I'm gonna step it one by one just to kind of break it down, and so we can talk about it in steps. So first step is we lose power. And so the power to the power supply goes away. And at that same moment, what's going to happen is, because the power supply goes away, we lose our signal. The interactive inverter also turns off. Now, this is where the rapid shutdown part of it comes into play, because without module level power electronics, or without rapid shutdown, as we all know, those conductors from the PV array all the way to wherever that inverter is, those are still hot. There's still full voltage on those. And so what ends up happening is because the signal went away, then our module level power electronics turn off. In this case, and again, I can't speak for everybody. In this case, I will speak to a Tigo specific thing. And Greg, please chime in here. But the Tigo MLPEs are designed such that if they don't have the signal, their default is off. So they will not allow voltage. They will not allow current to pass through. The modules are still hot. The module input on the input side is still hot, but the output side is not. So this gets into commissioning and stuff as well, which I don't know if you want to talk about here, Greg. But and again, I won't speak to other MLPEs how they actually do it, but that is this is the way Tigo does it.
Yeah, no, you hit it. So like think of each one of those MLPE as a normally closed switch, and so they need the signal from the PLC, which we call a keep alive signal. I keep wanting to call it a heartbeat, but it's a keep alive signal, right? So it goes through, and as long as those MLPE see that keep alive signal, then they close their relay and they are allowing the module voltage to flow through them. And then you connect the MLPE in series. And so, yeah, you got full string voltage at that inverter if the PLC has power.
Right. Or, and we'll get into some of these other potential issues. Maybe it's too far away or something like that. The signal can't quite reach it. Too many conductors. We talked about the 10 conductors. So there's ways where the signal may not be reaching those MLPEs for some reason, or we have the crosstalk issue, which is what we're going to kind of show you all now, which would in effect have the same issue. So here we have.
Sorry, before we get there, I want to reiterate that there is no chance of crosstalk. If this is a residential small system, you're good. You don't have to worry about none of this.
Right. Yeah. If you have if you're using the Tigo system and you have 10 strings or less, you really shouldn't have this ever be an issue. So here's another situation actually, and this is a product that you can get, right? The transmitter that has 2 CTs. So you could actually double what I just said. You could have 20 circuits, 20 source circuits coming through these, because you have a transmitter that has 2 CTs coming off of it, and you could put 10 conductors through each. So again, depending on the size of your system, how the inverter's connected, all that kind of stuff. Again, single inverter, multiple transmitters, but it's actually, it's a single inverter, single transmitter with multiple CTs is really what this is. And so that's going to be no crosstalk issue. And we're good to go however you wire this guy up. Is this one that you're seeing a lot of, Greg?
Oh yeah. Yeah.
Okay.
I mean, my alma mater SMA, the core, that thing has so many strings on it, it's ridiculous. So if you're using that product with this transmitter, then yeah, this is certainly something you would run into. So, as we talked about earlier, RTFM, just make sure that you're following all the directions in the manufacturer's manual for stringing and how many go through and all that, and you'll be fine.
Yeah. So in this case, running the conductors together, not a problem, because it's the single transmitter giving that single signal for that.
Yeah. Good to go.
Great. Okay. So let's get a little bit more, I guess complex. So if you have multiple inverters, so now we're getting into, probably the more common commercial size systems that we're seeing where you have multiple inverters in there. And I think we should start off with a point, because I had to get this clarification from you, Greg. When you have multiple inverters, each inverter needs its own transmitter. Is that correct?
Correct.
So you cannot share a transmitter with multiple CTs across multiple inverters.
Cannot do that.
Okay. Okay. So when we have multiple inverters, we will have to have multiple transmitters. And so the idea here is, if you have those inverter 1, 2, however many, 20, 25, however many it is, you have the multiple transmitters. And by keeping the conductors, keeping the raceways, at the keeping the distance separate, keeping all that stuff separated apart from each other, you're not going to have the issue of having any sort of crosstalk issues because they're physically far enough away from each other. 8 inches, is that right, Greg?
For us, it's 8 inches.
Okay.
And so that, it's just something you have to think about. So, if you wanted to cherry out the runs, you would just kind of bundle them all together and keep them nice and straight and, zip tie them up or whatever you want to use and just keep them on opposite sides of that cable tray and they'll be fine.
Yep. And we have a good picture where I was getting stumped on before I knew a crosstalk had a name up on a job site where I was doing that. So we have some pictures to kind of help illustrate that a little bit. So yeah, all's great here when you're doing that. Where you do run into problems is if you are, and this is, you're trying to run the conductors together. You have cable trays up on the roof, or you have, even if you're running EMT or you're running your conductors inside of a pipe, even if you had, array 1 and array 2 separated with a walkway, it sure is a heck of a lot easier to bring them to a single point, run a single pipe all the way back to where the inverters are located, and then branch them out again. And that's where you're going to come into the problems. And so this is where that crosstalk, you've introduced transmitter 1 and transmitter 2. This is exactly what we talked about when we showed you crosstalk to begin with. You're going to get induced signals, and those MLPEs aren't going to know what to do. They, probably best case scenario is they just won't turn on. And then of course, everything's wired right. You think everything's great. And so it's, whose fault is it? Is the inverter's fault? Is it MLPE's fault? And it just becomes kind of this, this is the app, fixing it after the fact. This is the con part of it, right? It's hard to fix it after the fact.
Yeah, nobody wants to go back up there and have to rip modules up and pull things off. We've seen varying degrees of kind of pains in the buttses, right?
Mm-hmm.
Like they don't all work right, or worst case, we have the thermal event, which is what everybody commonly refers to these things as. And it's not fair to just say, read the manual, it's in there, right? Like there's a reason why companies have sales engineering and pre-sales and online training and manuals and things like that. So, there is some responsibility that lies with the installers. And just because you're used to installing somebody else's product doesn't mean that all of those skills transfer over. I mean, the skills may transfer over, but there may be different ways of doing things, right, between manufacturers. You just have to take their training.
Sure. No, that makes sense. And that's a good point. It's reading the manual. Sometimes it's easy to miss stuff. I'm guilty of that. Right. I mean, and so it's easy to miss it, or to like, yeah. I've done this on this other system. I've got this, no problem. Just to come to find out it's something you should have gone left when you went right. So. Yep. Okay. And so then, let's talk about, we can multiple inverters, multiple transmitters per inverter. So getting into much larger systems here. So again, we have the first inverter, all the conductors on that single transmitter, no problem. We can run those together. So we'll truncate this array a little bit and we'll add another system or another inverter that has same kind of thing. And again, keep everything separated. You're great. You're fine. It's when you start to try and bring things together, when you're trying to, I don't even know how to say it without, you're using single conduit, single cable trays, that kind of stuff. And like Greg was saying, there's ways to do it. You just have to keep them separated.
Yeah. And I don't know if you were going this way, but like, this isn't this is totally understandable if an installer did this. If
Absolutely.
You're not aware of PLC, like, dude, I got one cable tray, freaking load them up, man. Let's go. Right. And so you're not being lazy. You're not taking shortcuts. It's just like, if you don't know, you're just doing what you've always done.
Yeah, no, and it was actually interesting. So the picture I'm going to show you is it was a relatively new solar installer. It was one of the cleanest installs I had seen in a long, long time. I mean, they did really, really good work. All of their pipe runs were great. Their work, and they had some cable tray in there as well. You know, they did a great job, and they just didn't know. And so it wasn't laziness, because they probably actually spent more time doing some of the things that they had done. But they were being what they thought was efficient. They were minimizing pipe runs, you know, run 1.25 inches instead of, you know, a couple 3/4. And just, they were doing things that made sense for them. And it just, unfortunately, just kind of came back around to bite them, because they didn't quite understand this issue. So you need to keep those separated. I think that's just kind of been the big takeaway that we've been talking about here. And we'll talk a little bit more about some other solutions here coming up. But let's talk a little bit about signal integrity. And so we've talked a lot, you know, all of that stuff was crosstalk, how you can avoid the whole crosstalk issue. And again, these values here that we're showing are Tigo specific. So again, if you are using other manufacturers, other PLC, make sure that you are understanding what their limitations are. So one of the limitations on the signal integrity is the length. And so if you go greater than 300 meters, and that 300 meters is a round trip, that's a circuit length, right, Greg? It's not a one-way.
Correct.
So, okay. So 300 meters of circuit length. So that's going to include all of your string runs, all of your MLPEs, and then coming back to the inverter. So, you know, as you pull the tape, less than 150 meters probably, but, you know, call it 150 meters as you would, you know, pull a tape measure or something. That would be for a single CT. You can double those up, and you get up to 500 meters. If I got that right,
That's correct.
Okay. So
and again, this is our solution, or this
yeah.
is our
Yep.
design criteria.
Yep. So exactly. So these are Tigo specific numbers. But that's a way of, you know, if distance is your problem, curiosity, Greg, I put you on the spot here. What if I'm more than 500 meters of circuit length?
Yeah. So it's like anything that doesn't get the signal. So the ones, it's just like an electrical network, right? Like if you have somebody that's way at the end of a line, they're the ones suffering the voltage drop, and they're the ones that have the appliances that wear out, you know, in 5 years or so. And it's the same thing with this, right? So if you go past the 500 meters, you know, round trip distance with 2 CTs, then it's those things way at the end that are going to start behaving erratically. And it could, like I said, it could be they just don't work right some of the time, or something really bad happens, and yeah, you have to send somebody out to replace everything.
Okay. So the solution is make that distance smaller? Is that, I mean, that
Dude, like, and you know, man, like, and you know, people will always push that, right?
Sure.
It's like, well, 500 meters. So, okay, 501 meters, like we can't do that, right? And so I would never try to challenge that upper limit,
Mm-hmm.
right? I mean, the engineers have to come up with some number,
Sure.
right? What they came up with, and it may or may not be conservative, depending on who the engineers are, right? So like my gut would tell me, man, if you can, you keep that within the 500 meters. Sure. Well, you know, 498 probably good.
So find a different route, find a way to move that inverter a little closer, run your AC a little longer or something like that. Yeah. There's
always a way, right? There's always a solution, and it's best to figure that solution out before you start laying pipe.
Right. Although it is easier to make it shorter. Although then you have to find the wire extender for the AC side if you move the inverter closer to the array.
Yeah, just pull it.
Those things are expensive.
Uh-huh.
Okay. So PLC transmitter, and this is something I think, Greg, we talked about earlier, or not earlier in this conversation, but as we were prepping for all this, you know, kind of an issue here is make sure your CTs are facing the same direction. If you put them opposite directions, they are a directional item. And so if you put them in opposite directions, then they're going to cancel each other out, and you're not going to get 500 meters. You're going to get 0 meters. And so make sure that you are probably an easier mistake to make than people even give credit for on that. Yeah. Relatively easy thing to fix, but still something you have to fix.
Yeah, sometimes, you know, PV inverters and micro inverters, and, you know, they all have some type of CT component to them, like nowadays. Mm-hmm. And if you're only using one CT and you know, reverse it, that's usually, you can on the back end just make a little thing and flip it, right? And you're fine. So the values don't show up negative. But if you do something like this, it doesn't matter if you flip it, right? You don't know which one, you know, is reversed, and the arrows are kind of hard to see sometimes. So yeah, it's an attention to detail exercise.
Sure. Yep. So lesson there is don't install these at Friday at 5 o'clock and or 4 o'clock, I guess. It's when you're doing those last minute button up items. So yeah, pay attention to that one. More on signal integrity. So we've talked about this. Again, Tigo specific 10 conductors per transmitter, only on a single side. And so, you know, the idea here is if you stuff it full, if you get more than 10 conductors inside that CT, the idea there is that those, you know, you're creating a bundle, and it's the inside conductors of that bundle can't receive the signal. It's just not strong enough to penetrate through all of those conductors and get to those the core of that bundle, and expect that those be able to carry the signal out. So that's, I don't know if there's more to say about that one, Greg.
It was pretty easy. And when I said this before, now I feel like I got to go run out and get some red vines. We just had this issue. It was like 3 or 4 weeks ago. And yeah, the guy jammed like 15 or 16 conductors. And yeah, so the ones in the middle weren't, it was a signal integrity issue, right? Not a crosstalk. Right. It was 6. We just add another core, split the conductors up, good to go.
And actually, so that's a good point. I'm glad you said that, Greg, because it's, you know, we were talking about, I mean, crosstalk was kind of the focus of this presentation, but then we've moved into the signal integrity. And so this by itself is not a crosstalk issue, but it's, I mean, they're adjacent, right? Because you've got to maintain that signal in order to get to your MLPEs out there.
Yep.
Okay. So here's an example, and I'm going to kind of pull up a couple of these arrows here so you can see. So just so to orient folks on what we're talking about here. So here is real world array. This is a roof that I was up on looking at this system, core 1 inverters, and the system just would not, we couldn't get it to commission. It just would not turn on. And so, you know, what we're showing here in this picture is we have some conductors. We have our source circuit conductors that are going up to inverter 1, some that are going to inverter 2. And as you can see, what we've been talking about, they have those 4 pipes coming in, and they're getting split. So, you know, even those pipes probably should be spaced out. Is that something you would say, Greg?
Yeah, I mean, I'm a big fan of comparable troubleshooting, right? So like I would separate, I think you're going to get to it, but like I would do it in chunks, right? Like separate the conductors first, and see if it works right, because man, moving pipe around, that gets intensive. Yeah. But it may be, you may have to do it.
Right. So I'm just thinking, had they had the right training, had they known about this being an issue, you know, if those top 2 pipes are going to inverter 1 and the bottom 2 are going to inverter 2, and, you know, they knew about this, probably could have separated them out at the array, kept them on either side of the walkway. You can see there's a walk path there. So I kind of remember this site a little bit. So they could have kept those on opposite sides of the pathway, would have been just fine. Then could have come to that cable tray at opposite ends, and they would have been probably more than fine. yeah, so right there, they have all those conductors from the different inverters getting different signals, two different inverters, two different signals. And so it's those conductors that are right there have that potential crosstalk. So,
Yep.
yeah. So as Greg was saying, if possible, it could have been moving those conductors over. Right where that arrow is for a 2-inverter 1, though, you can also see that those conductors cross right under those. There's a cross point there, so might have been that whole cable tray might not have been accessible for them to move that around. But nonetheless, just things to be considered during the installation process as you're going through it. Okay. So let's talk, Greg, tell me about some of these issues are. What's going to happen if you do have crosstalk? I mean, so we talked about, the inverters just don't come, or the MLPs don't come on, and what else could happen?
Yeah. And I mean, all of these things are true, right? Like there's so much that can happen when you have some type of intermittent signal integrity issue, or, the crosstalk, or anything in between those two. Right. And so the MLPE or whatever you're using, it may not be able to connect. In other words, for ours, the little relay may not shut to allow the voltage to come through. Right. Worst case, it may chatter. It may just
Okay.
like that. Well, those relays are not made to open and close 1,000 times, billion times a second, right? And so that's going to stress the electronics, right? Now that's the absolute worst case, right? So when somebody shows me a phone picture of something, with a TS4, a burned out hole in it, that's probably what happened.
Interesting.
Yeah, I mean, I think it's fun. Like it's fun to me, like, to troubleshoot these things. And I'm just like, we send people out to these large sites because there's a lot at stake, right? You got 250, 1 megawatt, 5 megawatt, 12 megawatts, right? Like, people want answers, and it doesn't look good for our industry when things burn up. So we're not like trying to, like, it's not culpability. We're not, it's your fault. Like, that's not what we're trying to do. We're just trying to get down to the bottom of it. And if it's something that, falls on us, then, man, we're going to pony up. We're going to own up to that. But then we also expect the same kind of responsibility from the installers, right? And if you didn't know about this crosstalk thing, that's just ignorance, and that's fine. Like, you can fix ignorance, right? That keeps you and me gainfully employed, right? But the other end of it is the component failure, the system goes into shutdown. Like, that's what you hope happens, right? That it's just, okay, I'm not working anymore. Right? So that's an easy thing, right? It's a heck of a lot better to start there than the other way.
Sure. So that's actually interesting, because you had mentioned the burned out, or seeing, failed components. And so I hadn't quite put it together. I'm like, how could this fail? Because I'm thinking, it doesn't get the signal, it doesn't get a right signal, it just opens up, and you're just sitting in an open circuit, or, well, the modules are sitting in open circuit and there's no voltage getting passed through. But that makes a lot of sense. If they're getting something, they're getting some sort of signal, and they're trying to connect, but they don't quite know, and they disconnect. And so that makes a lot more sense for me now on why we would see failed components.
Okay.
Yeah. So, and as it showed up for me back, that last slide, when we were looking at that, it was all about the commissioning, because, again, the system just wasn't turning on. We couldn't get it on. And the thing that was just throwing all of us off was, finally got on the phone, stuck tail between my legs and called tech support. But it was interesting because every single inverter individually would start up. We would just turn on, there were 6 inverters on site, every single one. You turn it on, go through the startup procedure, it worked like a charm. And go to turn on number 2 wouldn't turn on. Number 3 wouldn't turn on. But shut down number 1 and turn on number 2 by itself, not a problem. And so it was, as I've learned about it, it's like, if I had known it that day, like, oh, this is Crosstalk. But and like I said, I didn't even know what the name was. I don't even think when I talked to the folks at tech support that they had a name, but they knew how to help me, and they knew what was going on. So it was interesting.
Yeah. And something else that's a tattletale for some type of crosstalk issue is the particular model here that only does rapid shutdown is the TS4F. And so that ships in the off position, right? So it's the relay is open. And so, but it does allow 0.6 volts to pass through. It's this very small amount of voltage. So
Okay.
if you're, and we get this call all the time, hey, I just commissioned this system and I'm getting like no voltage at the inverter. It's like, well, what is the voltage? Can you divide that by 0.6? And does that number equal the number of modules up on the roof? Oh, wow. Yeah, it does. How did you know? Oh, okay. Well, your RSS transmitter doesn't have any power.
Okay.
Yeah.
Interesting. Okay.
I wish they were all like that.
Right. Exactly. Okay. So, I mean, all these issues, that we can come up with, if you're, again, your power supply is on, but you're getting crosstalk. And so the MLPE's best case scenario, you're getting, very, very low voltage. Kind of helps you see that. Absolute worst case scenario is you actually get some component failure because of that issue. Okay. So keeping those conductors run together. Sorry. Running those conductors together is kind of part of the issue. And so the last thing that I wanted to talk about is, this. So, Greg, I'll let you speak really to it, but the pure signal. So talk us through kind of a pure signal is what that means in relation to everything that we've been talking about now.
Yeah, so we have an awesome marketing team because I would not have been able to come up with this pure signal technology. I mean, it takes me like an hour to come up with a new gamer name every time I play a new game. So like, I'm not very creative, right? So what we did was essentially give a massive upgrade to our RSS transmitter and give it the ability to sync to other transmitters. And what we've essentially done is eliminated this crosstalk issue, because all the transmitters now, regardless of how many inverters you have, how many CTs or transmitters, the signals are all synced. They're all synced together, so they're not, in different times, different amplitudes, different whatevers. They're all the same. Yeah. So it doesn't matter if you put them in the same conduit or overlap them in the same cable tray. We just don't have this crosstalk issue anymore. But there's always a caveat, right? That last statement there, 10 transmitters, right? So that is the limit. So if you had 10 inverters with their own transmitter, then you can kind of disregard all of that stuff that we've been talking about before. However, if you have another 10 inverters with their own transmitters, those 10 can sync on the first 10 inverters. The second 10 would be able to sync, but we cannot sync the two groups of 10. So now all that stuff that we talked about earlier, all that still matters.
It's still in play.
Yep. Separate them out. Yep. But at least we've reduced the number by 10.
Sure. Well, and so it seems to me like a best, and I don't know how you feel about, best practice. It's, kind of like, code, doing something code minimum, great. You got a C minus. If you were to take it that next step, even those 10 that are using your pure signal, if you can keep them separated, all those kinds of things, seems like it's a better solution.
Absolutely. These are, and they're 20-year systems,
right?
So why wouldn't you want to do what the manufacturers? And I hate guidelines. I hate that word. I hate rules of thumb. I hate all that, because that to a lot of people that seems optional. right? So
Mm-hmm.
Tigo, and I'm trying to get everybody, trying to get them to use the same language. I call it design criteria,
Sure.
design requirements. Like, you have to do this. Yeah.
Sure.
And if you follow our design criteria, man, you will have a 20-year system that you will not have to go back and dork around with because you got two wires that are connecting to each other. It's just dumb.
Right.
And one more thing before we leave this slide. But yeah, we had this leader follower mesh, or not mesh, that's the third word, architecture. Yeah. So the first transmitter that turns on is the leader. And so that is the transmitter that tells all the other ones how to sync up. And so that kind of implicates that there is some communication wiring between the transmitters. Otherwise, how would they be able to sync up?
Mm-hmm.
And so that's what happens. And there's a lot of intelligence built in. Like, this is patented. And if the leader transmitter fails, or pick your doomsday scenario, a zombie comes up here and starts chewing on it, that's okay. Then one of the other transmitters will take on that role.
Right. So it can pick up. So right now we're showing the leader PLC transmitter connected. We're showing a purple line there. So you have some sort of data, hardwired data communication between those two. And if the leader PLC is on a different circuit breaker than the follower, and somebody goes and throws the power supply on the leader, but not the follower, then you would lose the inverter number one, you would lose that signal, but inverter number two, that follower then becomes the leader, if I understand it right.
Yep, correct.
Yep. So that's the other big key, is you actually physically connect those guys together. So again, and is there a limitation on that? I mean, so you said the 10 transmitters, that's really just, is there a length or anything like that people need to be worried about?
Yeah, what is the length of that? Like, gosh, it's longer than you would ever,
Okay. So that's, sorry, put you on the spot, but that'll be documented in the manual too, I'm sure. So
no, and I have a number, but I don't want to say it because of that law of privacy. If I say it, then that's what they're going to remember. And if it's not the right one, then, well, Greg said, and then
Greg said that. Yep.
Yeah.
Look in the manual. Look in the manual for your lengths there.
I'll take that as a lookup.
Cool. Okay. Well, before we go away from this, wrap anything up, you have any other final things, Greg?
No, this has been just awesome. The pictures clearly show, what we've been talking about. Yeah, I love it.
Cool. Well, so that wraps it up then. So really appreciate you taking the time, Greg. And hopefully you all walked away with something helpful here on the crosstalk, and picked up maybe some little tricks if you're up on a roof and something goes a little bit awry. You'll kind of troubleshoot that a little bit better, or even better, working with your crew, installing and saying, nope, we gotta run those pipes separate, or keep those conductors separated, things like that. So appreciate everybody's time. Our contact is here on the screen, so if anybody has any questions, comments, Greg would be happy to take all your questions.
Send them to me.
I'm happy to talk with folks as well. I just like to give Greg a little hard time. Appreciate it. And thanks, everybody.
Awesome. Thanks, Ryan. Y'all take care.